into the free and open source software space now, and I'm an avid Linux user, running Linux on my Mac. Which is a lot of pain. My favourite languages at the moment, well, my favourite language is Go, but I'm a big user of Orca and Bash. I enjoy testing kernel patches and tinkering with new technologies. I've been working on the Elasticsearch stack, well, the ELK stack, for a couple of years, and I am literally terrified by the thought of public speaking. So, cut me a bit of slack. All right, so I'll tell you a bit about our logging problem at UQ. This might be familiar to some of you. Reacting to problems using monitoring and alerting is we have done so in a traditional way, using basic scripts to monitor things, and that's kind of limiting. Logs are typically scattered and they're across teams and servers, really difficult to figure out why things are going wrong. Logs are also terribly inconsistent. The formats are totally different. We've got different retention periods for different servers, different teams. Nothing's standardized. We have a lack of quantitative data to gain business insights. How are our services running at the university? Very difficult to determine, is it running or is it not running? Often if we need to investigate something, it was using bespoke scripts, which are typically once-off, time-consuming to write, and answering questions really slowly. We've had previously tried to collate data, like our wireless authentication radius data, into traditional databases. Extremely slow to do queries over our data set when you're talking terabytes of logs a month. So it doesn't scale, totally inflexible. We also ran Hadoop, but once again required quite a lot of time and requires predetermined outcomes.
Oh man. That's very
You can do it.
One moment, please.
Here we go.
It'll start.
Start it.
Back.
It's Google, it'll work.
Though it's running Linux on the Mac. So
That's true.
It's my fault.
That's my fault, sorry.
Stop. Close. Stop doing what you're doing. I want to cast tab and I want to do it there. Cool.
Turn off running again.
So we played around with Hadoop. Time consuming, required predetermined outcomes, and didn't really solve our problem. It answered some question with our wireless stuff, but it sort of showed a bigger problem for us. So we had a look at what we could do for central logging. Obviously there's quite a few modern solutions out there. Like you might be familiar, you've heard about Splunk, Greylog, Loggly, and the Elastic stack. They all had a range of various things, but the attributes, but the biggest thing for us was that the ELK stack was open source, it was free. There was commercial support there if you needed it, but the biggest thing was that there was a vibrant community, and being at a university, we tried to get involved in that where we can. Another big thing was looking at Google Trends. We can sort of see, like Splunk sort of set the way, but the Elastic Stack has really gained a lot of traction and popularity when it comes to Google searches. So that gave us a lot of confidence in moving forward that there would be a community there to get involved with and to support us. So the Elk Stack. So it's now comprised of 4 open source products: Elasticsearch, Logstash, Kibana, and Beats. Bit of confusion these days whether it's Elk, Elkbee, or Belk. But as of version 5, they renamed it to the Elastic Stack, so I need to get into that habit. And all these together form a central event logging pipeline. So Elasticsearch, I'll just give a bit of a basic rundown of the products. Distributed full text search and analytics engine. It's built on Lucene with a RESTful API. Data set is JSON and stored in indices. And index is comprised of shards. And each shard itself is a Lucene index, and shards are spread across the cluster nodes. And primarily replica shards with routing provides redundancy. Writing a document to Elasticsearch is referred to as indexing. Like just a bit of comparison, a document is like a row, a traditional database with more flexibility. An index is like a table. And JSON keys are similar to column names, and each has a data type. Data saved in an inverted index, which gives us fast searching. For each word, the IDs of the event that contain the are listed. Enabling doc value stores an additional columnar structure, which helps with navigations. There's no transaction log, eventual consistency, and we treat Elasticsearch at EQ as non-authoritative. So we kind of see for us Elasticsearch as being an analytics tool, and we also would always want to go back to our sort of source of truth, which would be the original ones. Creating an index in Elasticsearch, got a bit of a demonstration. So we are basically using our put command, and so we can create a new index. And when we do that, we get 2 primary shards created on the cluster. Those are allocated to different nodes. We'll add some replicas, and so our primary shards get replicated across to our other 2 nodes, give us a set of redundancy. One of the nodes reboots for patching, which happens for me every 3 months from our infrastructure team. And then if we haven't told it not to move the replica, then we'll get our redundancy with that shard now being replicated across to another node. When the other node returns, then it rebalances and our shards are nicely distributed across the cluster. Indexing and searching is really easy. So we're just putting a document in, just in a basic JSON structure so it's fairly straightforward, into our index and type and document ID. And then doing a search is really straightforward with URI queries. We sort of get a structure back like so. So that's kind of the very basic crux of Elasticsearch, which you may already be familiar with. This is a bit of an example. It might be a bit hard for you guys to read with this projector, but basically we this is like an example radius log, which is a wireless authentication. We've got a couple of notable fields like our destination objects. Beneath that we've got basically our IP field. So if we've got a remote request coming in, we can see the IP address of the person requesting authentication, say to our VPN service. And then we've used the GIP filter in Logstash, and that's populated our GIP location information so we can plot where our requests are coming from. And this is kind of a bit of a standard structure that we use across all our logs, and that's really important for us to be able to compare our information across different services. Having a standard way of indexing the same data with the same key names is super important. So Elasticsearch is really awesome. It does have the ability to be schemaless. So you can just start writing data to it and it will index it and automatically detect the value types of your keys or your fields. We found that an overarching scheme is required for central logging, just because it made it really difficult to compare services, and so that common data between events enables correlatability if we have named everything and labeled everything the same between services. So we achieve that using index templates in Elasticsearch and a data dictionary, which is something we've defined as a group and basically said this type of data will exist in this field name and have these formats. So as we're adding new log sources into our cluster, we review the data dictionary and just make sure everything's adhering to that. Index template enforces the data types, particularly for the common ones we're concerned with. And our data dictionary defines the field names for each data type. So Logstash, open source server-side data processing pipeline in Java. So we can ingest events from multiple sources using a variety of input plugins. Very rich ecosystem for Logstash. I use it to transform and enrich our events using filter plugins. Some of them are Grok to do our sort of regex-like field allocations, mutations, so we can mutate field types with, for instance, do reverse and forward DNS lookups, resolve geolocation information with the GIP filter, and yeah, the list goes on, but those are some of the common ones. And there's an extensive selection of outputs, so obviously to Elasticsearch, which is what we primarily use it for. You can send to other Logstash instances, to Redis, which we use, and like a variety of other things for testing. In our case, like if I want to develop a new filter for a log, then I will use the file output and check out what's going on with our processing. It's simple to understand configuration, and that makes it really easy for people and other teams to get up to speed with how to process their logs and get them into our Elastic cluster. It has configurable performance tuning, so you can, depending on the cardinality, the type of logs that you have, you can performance tune how, like, the best indexing performance for your Elastic cluster. So beats are lightweight, single-purpose data shifters. So this is what you run on your servers to send logs to your Elastic stack. Send event data from Logstash to Logstash or to Elasticsearch directly. It has an extremely small footprint, which makes it very useful, particularly if we're doing, like, for example, it was quite a hard sell to try and tell our Windows admins that they need to run this giant blob of Java on their domain controllers. but running a nice little lightweight binary in Go was a much easier sell. It just sits there and does its job really well. WinLog beat is really awesome. No runtime dependencies, so super ultra portable, written Golang, and there's quite a few beats available written by Elastic and quite a few maintained by the community. FileBeat is one that we would quite prominently use, which just sends logs from files. WinLogBeat will integrate with the Windows Event Logger, so we can ship our 80 logs. And there's a bunch of others, like MetricBeat will give us like information about like combined top beat, and a few others to give us stats on our hosts. The LoopBeat framework is available, so developing your own beats is quite easy. It really lowers the sort of barrier to entry to sort of contribute to the ecosystem.
Is that an official Elastic logo up there in the top right? And do you have stickers of it for the rest of us?
We can make it so.
Very cool.
So Kibana, this is what we use to visualize the data in Elasticsearch. What you would use to explore once you've got your data in there. It's simple to use interface, and it integrates with the RESTful API of Elasticsearch. Discover and filter your logs by searching with a simple query language. From your searches, you can create graphical visualizations with dynamic queries. Combine separate queries into a single graph using timeline, which is really awesome feature. Combine visualizations to create your dashboards. We have our dashboards up on TVs, and like within each team we have interesting dashboards, metrics they like to keep an eye on, so they can come in the morning, look at the screen and go, yep, everything looks like it's running as per normal. Handy developer console for DSL queries on the RESTful API really makes writing querying Elasticsearch super easy. So that's also another great addition. So this is kind of just to review the logical Elk stack. So we've got our servers running beats. We've also run other shippers, say just like a Logstash, for instance, on our Solaris boxes, because Go wouldn't compile for them. Damn you, Spark. So our beats obviously are sending our logs into Logstash. They're being processed, being indexed into Elasticsearch. And then I come along and have a look at Kibana and explore and create awesome visualizations. So our Elastic cluster is comprised, we've got 4 physical boxes. They're Dell PowerEdge 730 XDs, kind of getting on a little bit now. Each of them has 28 cores, 192 gig of RAM, and 8 1T 10K RPM drives. They're in sets of two RAID 0 arrays. So we want to get the maximum performance out of our disks, and we trust that Elasticsearch is going to handle all our redundancy for us. So for our cluster, that gives us 140 physical cores, about a T of RAM, and 40 T of disk. So our logical backend is a little bit more complicated than the basic pipeline. This is probably something which, if you've got a great amount of logs coming in, this will be something that you'll... one of the big issues is if we have a lot of logs coming in, we can't process them with Logstash in time. So we've implemented the Redis queue that queues our logs. Or if, for example, someone changes the logstash config for our logstash processes, that breaks it for whatever reason, and somehow it gets into production and we can't process logs, they'll just back up nicely and read us. That's a really great buffer for us. Our logstash processes read from our ES queue, do all our transformations, and then on each physical box we have one master node and 2 data nodes of Elasticsearch. So that gives us a total of 15 nodes. And in my environment I'm using Docker, so I containerize all of these containers on the logical backend, and I'm using XLD and Fleet, and that basically allows me to orchestrate the starting and stopping of containers across the whole cluster with ease. This is a look at our logical front end. So in front of our web access, we've got Nginx. We protect that with our SSO, so our UQ single sign-on, which is a common authentication method for all our applications these days. Then we wrote this really terrible thing in PHP that it basically acts as a access control proxy. And so based upon your username, your group membership and Active Directory, we can limit what indices you have access to in Elasticsearch. It's a little bit dirty, but it does the job for the moment. And then we are filtering the requests going through to Kibana, so, and that also in turn limits our view in Kibana. Then obviously Kibana is talking to Elasticsearch and returning data back to me, who's looking rather terrified.
It's a bit of PHP.
Yeah. Replace it with shields. This is some stats. This projector isn't doing me any favors, so sorry for that, but we're sort of maxing out about 33 billion events in our cluster. That gets us to, you can sort of see this sort of zigzag pattern. I'll sort of explain that in a second. But basically, there we go. And this is our cluster size. You can sort of see like the upper limit there is about 32 terabytes. And so obviously we don't want to consume all our disk. We need to handle a node falling over, like a physical node. That's 2 data nodes. So that's basically a fifth of our data we need to have. Like we need that space available to replicate in case of failure. And also we want to try and keep our data from not fragmenting too much on our Linux file systems. So try to keep it around 30T. I'm using Curator, and that every month that sort of closes off our old indices and waits a bit and then deletes them. So we've got about a 7-day grace period between when we close off the index and when we actually delete it. And so that sort of manages itself. And Curator is a really cool tool that was written by someone at Elastic. Totally recommend it. It's really really takes the effort out of worrying about your cluster growing GB. So some of our counted problems. Trap for young players. This may not be the case anymore, but when I started Logstash, was doing daily indices, and so what that resulted in was leucine index, like basically 10 leucine indexes every day, and that adds up over time. So we have like 1 trillion file handlers, all this resources being handled by each leucine instance. And so given a relatively small cluster size, I think we were sort of approaching 10T, we're getting Java out of the mirrors, which was really, really annoying. But at the time it did make a lot of sense. Like the more shards you have, like surely the faster it's going to return it up. And we sort of learned that the hard way. searching with index patterns. That was previously hitting all our all indices, so all of our daily indices were being hit when we wanted to do searches. That's been fixed in version 2, where now the metadata of your index is now stored, so the time range. So if you're doing a time-based query rather than hitting every index, we're now hitting only ones that matter. Big queries and field data were another big one. We had a lot of cluster instability if we were searching our whole breadth of data, and doc values really helped with that, moving letting the Linux file system cache in memory handle a lot of that, which has been helped us out heaps. Another trap was early on in the piece, because I was running Docker containers, I thought, well, masters are just not that important. Surely the cluster state is stored on every node, but as it turns out, at one point in time we had an issue where all our Docker containers stopped, and when we restarted them, we actually treated them ephemerally. So all the Docker container instance disappeared, and as did our cluster state. So even though we still had all the data in place, so always make sure if you're running Docker, always a great idea to map your volumes and keep them on, keep your data persistently for Elasticsearch. Dots in field names, that was painful, going from version 1 to version 2. And what was even more painful is that we decided, okay, we'll just start again, and then shortly after that, they were now allowed again. So that was a bit of a problem we came across. Also, previously, Lucene used to shard for us across just basic disks. So rather than having our RAID 0 arrays, we just could say, write to these disks, and Lucene would shard across those. Obviously, that came at the expense of file handlers as well. So they moved to having a single target for each shard, disk target for each shard, and so therefore we moved to RAID 0 arrays for each data node. So for each of our one data nodes, they have one RAID 0 array behind them, and they just write to that exclusively. Keep alive D. That was not good. That's more of a Docker problem. So when one of our Logstash receivers went down, we had a floating IP that would go across. The reason we did that was for old log shippers, and they were only able to send to one target, so we just had like one DNS address which resolved to a bunch of floating IPs, and so you could always get to an endpoint if one of the receivers went down. And currently we have no query-only Elasticsearch nodes. So what that means is because our Kibana instances aren't aware of the cluster, they talk to a particular data node, and during patching that means the Kibana instance is offline. So we currently run about 10 Kibana instances for each team. They have their own Kibana indexes with their own dashboards and visualizations, and kind of keep everyone in their own little space, their own little sandbox. So that's sort of a bit of an outage, but fortunately it's not a mission critical system for us, so if it's out for 10 minutes it's not much of an issue and no one notices too much. So our process for putting new data sources into our cluster, for each team we have in ITS, which is the central IT group at VQ, I try to train one champion, and they're the person who understands about Logstash, how the Logstash filtering works, and they know their logs. Like I don't know the applications they're writing. They know what type of insights they want to get out of it, so bringing them up to speed helps spread the knowledge. So that's the approach we've chosen to go for, rather than me write filters for everybody, which makes me a single point of failure. So we start off by getting a sample of their logs. We sort of run that through a beat to a file output, so we've got this basically a replication of what we're going to be sending to the cluster. And we use that as our basis for developing our Logstash files, simplify our customization. So having, like basically I've got one config for all our Elasticsearch nodes, even though they're master or data. I've got like one config, and when I deploy it out, it's aware of what it's doing, where it's going, and what its role needs to be. All our container config is version controlled in GitLab. Jenkins builds and basic tests new config on pull requests from our contributors or myself, and then pushes the Docker repository on merge accept. Then there's that deployment, and so that automated deployment I'm doing with Fleet, and so we have etc. D, which is a distributed key value store that keeps our state of which systemd unit files are assigned to which node, and so I can basically say start me 5 Elasticsearch data nodes, and it will just go, okay, cool, I need to start one on each node, and we'll go ahead and do that for me. So it gives me a single point to control our Elastic Stack from. As a matter of fact, I can do that directly from my laptop without having to SSH into any of the machines directly. Makes it super handy. So obviously we have a private Docker registry to keep our config and containers in. We have the curator, which we use to automatically delete the old indices, keep our cluster size under control. I've set up a read-only Elasticsearch API using Nginx, and that's basically so for teams to run scripts, query scripts against, and they can't accidentally go and delete stuff, which is totally possible. I use Cerebro, which is kind of like an Elasticsearch web admin tool. Gives you a great overview of the indexes in your cluster, how your shards are allocated. Also has a query interface, allows you to manage your index templates, and it's like really quick to look at and go, this is what my Elastic cluster is doing. So we've also had a need to do metric monitoring and alerting, and obviously I don't want to log into the cluster itself. So I've just got an InfluxDB instance which can logs metrics about how the cluster is running, and I do that with Grafana and have some alerting thresholds. The biggest one I care about, apart from our space allocation, is our JVM heap usage, and so I get alerts on Slack, which just lets me know, hey, your JVM heap's getting too big, or your cluster's getting too big. Or your Logstash processes have stopped processing for some reason, or your read SQ is going out of control. So I use Telegraph to aggregate the metrics. The metrics are sent using the statsd plugin in Logstash, so that gives me our pipeline, some basic pipeline metrics. I aggregate that and store that in InfluxDB. I have a private Slack for receiving visual Grafana alerts. That's really great. I could be on holiday and I get a Slack alert on my phone and go, oh, something's wrong. I can quickly jump in and fix it if there's a problem.
Because you're involved.
I'm the single point of failure at the moment, so yeah. But it's all right. It really does look after itself. It's really well behaved. Most of the time, actually, my biggest problem is patching. So we also have a syslog server, so that receives syslog from a whole bunch of network devices, and then we send that across to the Elastic cluster. When that gets rebooted, obviously there's a big backlog of logs, things trying to send logs to the syslog servers, and once they come back online, they can sort of flood things, flood the read SQs. So I often get alert about that, but usually that's once a quarter. So kind of can anticipate that one. I've been writing some tools in Go. So we have quite a lot of requests from researchers at UQ to get access to data. So we've got questions like, how are our students, where are our students on campus? Like when are the most busiest times for foot traffic? Often we can infer that from their wireless devices, their wireless logins, and what access points they're connecting to.
Is that what the GeoIP data is you're referring to, like on-campus access points?
So that's kind of interesting. So our access point location data is not available in the GeoIP database. So we actually have to do a manual mapping of, basically have to ask university networks to give us information about where the access points are. So we're actually going through the process. They have their own Elastic Stack, and I'm going through the process of merging that in, and the plans to enrich our wireless logs with that location data and resolve those to geo points that we could then sort of spread across our camps, just to even get a vicinity idea of where people are going. But when it comes to researchers, they're doing their own thing. They really love their raw data, and so I was getting kind of sick of writing these bespoke scripts. So I wrote this tool called EScroll, and that handles my scrolling searches. So I can do one query, and it will just dump everything for like the breadth of our Elasticsearch cluster. So I've just done a dump for a research project, which was about 30 gig of data, and that is tool's come really handy. Also, user anonymization. So we also have a project going on at the moment with our external consultants, and so obviously we don't want to give them all our student information. So written some stuff to anonymize our data. So basically, as we're bulk extracting it, I can anonymize it in a consistent manner. So we're sort of sorting and hashing the data in a consistent manner with other data sources, so that we can then correlate, like we'd say, with the library's data on their logins, or who else have we got? We've got like student enrollment systems, and so we want to get that hashing in a consistent manner, so that when we're engaging consultants to do some big data analysis in AWS, we've got a common ground to work from. So these are a list of our existing data sources. There's quite a few there. Apache, Active Directory, Cisco firewalls, AWS CloudTrail, Blackboard, Auth, which is our student learning platform, Nginx logs, DHCP, DNS, our F5 load balancer, our IP tables in our physical machines, Kerberos events, so we have our own Kerberos systems.
Out of all of them, which one's the most interesting? Which one of these sources has provided the most interesting insights?
I'm definitely going to go with Radius, I'd say. I don't know, I think Radius is nice because Radius for us not only does it do wireless authentication, but it also does VPN authentication. And that is really great to visualize where people are connecting from to remote login. We also get a lot of visibility and brute force hacking on our Radius accounting stuff. So like you could just look at, like when you're looking at the visualization of successful authentication versus failed logins, and then you can also sort of show a list of IPs which have like the highest number of failures. So if you get a spike from one particular IP, it's quite obviously a brute force attempt. That would be also true for our web application logins. So our Blackboard authentication, our PeopleSoft authentication. So those logs are probably the most interesting to look at. But then there's also configuration issues. So like looking at DNS, for instance, we found that a lot of our authoritative DNS requests are coming from the US. And it's like, well, at least 30% of our requests are coming from the US. We don't have a presence in the US for DNS, so maybe it would make sense for us to put a DNS server to serve those hosts in AWS. So sort of understanding how your services are running, I think all of them together paint a picture. IP tables is another great one, because we have a lot of things that may be misconfigured, or like logs with like things which are sent into the wrong location, and you're just able to see them straight away. So I don't know, it'd be hard to pick one. Yeah, that's sort of where we are at the moment. Some of our future data sources, our border firewalls, Nmap port scans. So we've got a security group which doing scans of our network, and so just obviously getting that into the cluster and visualizing that would be useful. There's some additional university network device logs which I was talking about, which will help enrich our wireless data. DNS resolving records, that's starting to happen, but that's a pretty big fish, that one. Our SMTP mail hub, which is quite terrible, again very similar to our LDAP logs. So sessions exist over a period of time and all the events are interleaved, and it's sort of a bit difficult to piece back together. And Outlook web access logs. Or just all the logs, really. I'd be happy with that. So moving forward. So at the moment I've been doing, starting to get close in peak times to like our optimum, like I can get an idea of what our optimum event per second throughput is if I just let our readers queues back up, like turn off all our processes, let our readers queue back up, and then wait until we have several million events in the queue, and turn our log search processes on, and then I can basically see how many events per second we can index at. And it's been a little bit difficult because our pipeline is quite convoluted now. We've got lots of different filters for lots of different services. It's quite difficult to figure out which are our biggest consumers of processing power, what's slowing us down the most. And so I've been doing a little bit of performance profiling. We've got a joint Triton. It's kind of like a container cluster running in our School of ITEE. And I'm using Terraform to spin up some environments there, and Ansible to set up a test Elasticstack environment, and got some scripts to do our testing. So that's kind of giving us some interesting insights. And I'm learning a lot about how Logstash is working internally and what are some of its performance limitations. Yeah, that's an ongoing part for me. Improving our metric collection, but definitely the big data, the analysis aspect of our data set, now that it's all standardized in a standardized format, is something like this is a base for us to build upon and gain better business insights about how we're delivering education. So yeah, it's a pretty exciting project. Does that answer your question?
Yeah, thank you.
I got one more question. I'm biased, so take that into account, but why are you not using the monitoring plugin that leverages the Logstash APIs and building your own using the metrics? I mean, why not use Logstash APIs? Why are you using metric filter? And then why don't you just use, the things that we've released? Not open source, I totally get, but just interested in why you're building that.
Metrics is kind of like the monitoring of the cluster has kind of fallen by, like I've got other priorities at the moment. So this was kind of set up before that API was available on Logstash. I have used it as an investigatory thing, and if I find someone's having a problem with Logstash, I'll often point them in that direction. But it's kind of more of this is an in situ solution which is working for me right now. So yeah, definitely needs to be reviewed. And as I move these supporting services into our next gen, I hope to revamp all that. So yeah, I wasn't quite sure. Does it really give you a good understanding of like which exact instance of a filter you're calling in your config? Because I could never determine that from the whole thread stuff.
It may not be exposed in the monitoring UI side of things, but it's within the APIs.
Okay. No, I've had a good look into it, and it's just like, I don't know what instance of this filter is causing it in my massive config.
Okay, that could be.
Because it will say, oh, this is the filter that's chewing on your CPU, but it's like which of the 20 or 30 of those instances of this filter is causing that. So yeah, that's kind of one thing which at my first look I couldn't determine, but hopefully with the new pipeline feature coming in, the multiple pipeline feature, we can separate those out and use that a bit more effectively. That might be useful. Yeah, for the meantime, definitely that performance tuning project I've been sort of working on in my spare time has been at least giving me a good appreciation of how Logstash functions.
Are you looking at all to get rid of the Redis? Because with the latest beats and Logstash, it doesn't have reliable delivery and queuing and all that built in, and it says you don't need Redis anymore.
That's true to a point. One of the great things that we like with Redis, we actually have it writing persistently to disk. So as
so
the logs,
Logstash has that now, doesn't it too? It's got that.
that is a new feature that's come in. I don't know how much I trust it, and the fact that it's in a JVM. I haven't tested that out yet. I did notice that was a new feature. Once Redis has been absolutely bulletproof, and it has through my performance testing, it's not giving me any bottleneck in my pipeline at all, and it's been super rock solid. We actually had a kernel update that came through for Oracle Enterprise Linux, which with a combination of Docker and XFS, which we're using for our storage, caused kernel panics and random reboots. And it was perfectly rock solid for us in that situation. So super happy with Redis. I kind of think if you find something that works well for you, can continue doing it. But definitely we've got the Logstash receiver sitting out the front, and our idea is just to accept the logs as quickly as possible, remove any sort of bottleneck on our actual production systems, which are sending logs. We don't want them to be pulling out logs in memory, waiting to send them to our cluster for whatever reason. So